Hey there everyone, all the techies and data enthusiasts there. So guys, welcome back to another video of Transformers series, and in today's video we are going to discuss about encoders in Transformer. So encoders architecture, we are going to deep dive and discuss about it. It's a very important video. So previously I have already explained you all about adds, which is nothing but residual connection, and norms, which is nothing but layer normalization, and even feed forward neural network. Before that, attention, self attention, and multi-head attention, and many more concepts were already covered related to transformers, which is very important. Even practically also I have shown them. If you have not checked out those particular videos, do check out. The video links are in this video description. Make sure to follow me for more updates related to data science and AI, and do like, share and subscribe the channel, and share this video with your friends who want to learn data science and AI, and follow me in LinkedIn for more updates. So guys, now let's get started. So guys, you all can see the notebook here of video 6, which is encoders in transformer architecture. So what is encoders? We are going to deep dive in it. So in transformer architecture consists of mainly encoder and decoder. Each of these components is made up of multi-layers that process the input data. The encoder is responsible for transforming the input sentences in a continuous representation, while the decoder generates. In short, what encoder does is it takes in the data and it transforms, and decoder generates the output. So slowly, like all in our previous videos, we have created a separate diagrams and detailed explanation, right? So the same way it goes on here also. By seeing these diagrams, you will understand. Working with encoders, so input representation. The input is first tokenized into individual words or subwords. So as we discussed earlier, and in earlier instance in our earlier videos about this one tokenizing. So in transformers architecture, we have discussed on this embeddings and positional encoding, and after that self-head attention and multi-head attention. There I have explained them, what is QKV and why is it important. That also I have explained. Embeddings, each token is converted into a dense vector representations or embeddings. Then positional encoding, since transformers do not have built-in sense of order, or positional encoding are added to the embeddings to provide information about the position at each token sequence. In short, it is nothing but, I'll explain you all with this image. See, so input data, that is already tokenized input data. Tokenized, it nothing but it can be in words or sentences. So sentence tokenization is there, word tokenization is there, subword. There are many tokenization techniques are there. So it will be tokenized first input, then we embed those input embeddings. We create embeddings of it. And embeddings are nothing but a vector representation or vector mathematical numbers closely related to that. Like cosine similarity you have in AI, it is mostly used. Okay, cosine similarity. Those who are working on RAG, they will understand it very well, and even fine tuning also, of course. And positional embeddings. So we create positional embeddings. Why we mainly create positional embeddings is that in transformers, right, they don't have that sense of keeping this data in order. So they are not good at that. So that is the main reason we create a positional embedding, and we have them. Whatever input embeddings come in, they are already positioned or they are tagged with the position. Then multi-head self-attention. The encoder inputs are processed to the self-attention mechanism, which computes the attention score to determine how much focus each token should have, or every other token in sequence. So once the data is position encoding is done, then we process or we send it to multi-head attention. Here what it happens, multi-head attention creates a score or gives a rating or score, you can say, to each and every data which is closely related to that. So you have self-attention in this and multi-head attention. This is already covered in detail in video 4. So you can go and have a look on that. You will get a clear clarity about self-attention and multi-head attention. After that, adds and norms. After self-attention, residual connection and layer normalization. So as I told you all earlier, so go and check out the previous video to understand this in more detail. So the output from the multi-head attention layer is add back to the original input. So encoded input using a residual connection. Then layer normalization is passed and normalized and stabilize the training. Then finally, whatever we get, we send it to this first multi-head attention. Then after this, we send it to second multi-head and third multi-head. So this is nothing but multiple times. Like if you have checked my previous video, I told, right? First a multi-head attention process goes on, normalizes, then again feed forward comes in. So once the feed forward is again done, then we process the final data. So feed forward related, here you have a feed forward normalization. Feed forward is nothing but an ANN. You give and you pass this normalized data or stabilized data, whatever you get, to feed forward neural network or an ANN to apply the neural network process to understand the meaning. Then after all this, again you pass to residual connection, which is feed forward network, feed forward output, right? What you get from feed forward neural network, that you again pass to adds and norms, and finally you get the output, processed perfect output. Encoder output. The final encoder output is in sequence of contextual representation, where each representation captures the essential information about the corresponding input token and its relationship. While other tokens in the sequence, these encoder outputs are then passed to the decoder for future process and generation of the output sequence. So here you have a complete diagram now, see, to understand better. So we have an input data, then we pass it to input embeddings, and the positional encoding is done. Then after the positional encoding is done, we pass it to multi-head attention. So multi-head attention, you can have multiple multi-head attentions and layer normalizations. Residual connection and layer normalization is done. Then finally we send it to feed forward neural network, which is nothing but your ANN. Again, once we get the output from ANN, we again normalize it, adds and normalize it. Then from there we send the data to, once again, multiple times it goes on, and finally we get the output generated. So this is a normal process, you can say. This is the normal process what takes in transformers architecture. So if I open this book, so I guess in this only we have transformers architecture in detail. So in this, which you are seeing now, right? Yeah, here you have in smaller version. This you can have a look later, okay? So input you have the input embeddings, send the input embeddings and the positional encoding, then multi-head attention, so multiple times it goes on, then add normalization. From there again we send it to feed forward neural network, then again we get the normalized output, then finally we send it to decoder architecture. Okay, decoder architecture, so we will be covering this in our next video, okay, about decoder architecture. There I'll explain in detail. Before that, I guess we have masked multi-head attention, so that is also there here, multi-head attention. So that masked multi-head attention, so I'll explain about this, then we will go with decoder. Okay, so this, I hope this is very short video because we don't have much coding here like which we have in our self attention and embeddings to clearly work on it. But it's okay, you guys understood the concept, right? That is more important. So I hope this video is very interesting to you all. Do like, share and subscribe the channel, and you can check out this notebook in this video description. Make sure to fork the notebook for further references, and meet you all again in the next video. Bye bye.